So we're going to continue with chapter 4. We just started the chapter. And I just had a quick question. Has anybody in their experience used probability? Amir, when did you use it? Amir, when did you use probability? When you want to buy shares. Okay, can you give me a little more, give the class a little more detail about what you did? You can talk if you want. You turn your microphone on. So when you want to buy shares, if it goes up or down. Okay. And what was the time frame of buying the shares? Like, were you looking at 100 years? Were you looking at a year? You were looking at 5 days? What was the time frame where you tried to predict what the shares were going to be? 6 months. Okay. I just brought it up because probability is a method that is used extensively in business. Now, I don't come from business, and I can't give you specific details, but if you look at the text and you look at examples, it's used extensively because in business, well, just like any other area, you're going to have lots of data. And what can you do with that data? Analyze it. So, as Amir pointed out, people buy shares. The person, if it's a financial advisor, a financial consultant, a stockbroker, they're going to give you some information about a particular stock or mutual fund or anything else to invest in. You're going to want to look at the data. You want them to give you their analysis of the data. And as I've mentioned previously, you want to have enough data to make a rational decision on if you're going to buy something. So we haven't got into that yet, but can someone give me, what their feeling is on how much data is good data to predict something? Anybody? 100%? Well, that would be, when you mean 100%, the way I interpret that is it's from day one to the current. Yes, the more the better, exactly. So if you're in a situation where you are trying to purchase something, or you want to predict something that you're investing money in, you want as much data as possible. And if you can get all the data, even better. Anyways, let's continue. As I mentioned in the announcement from today, for sure we're going to be doing chapter 4 today and on Friday. I'm not sure if we're going to carry over to next Tuesday, so I extended the homework to next week. And it's a very important chapter because, as I said, it's integral in business. It's really important. So please, if you have any questions, ask them. Okay? All right. Just going to make the screen a little bigger. Okay. So one of the first things is an independent event. And events can be independent, meaning each event is not affected by any other events. This is extremely important. The coin, as in the example from Friday's class, doesn't know that it came up heads before. Each toss of a coin is a perfect isolated event, meaning it's independent. It has no relationship to anything previous or any relationship to what's going to happen after. So an example, you toss a coin 3 times and it comes up heads each time. So what is the chance the next toss will also be a head? The chance is simply 1/2 or 50%, just like any other toss of the coin. So what it did in the past does not affect the current toss, nor in the future. And some people think it is overdue for a tail, but really, truly, the next toss of the coin is totally independent of any previous tosses. So saying a tail is due, or just one more go, luck is due, is called a gambler's fallacy. Okay? So, I heard an example where they're talking about professional basketball players, and somebody says, oh, they're hot, or they're shooting whatever. They're getting 8 threes in a row, a 3-point ball. So, oh, they're probably going to get more of them later on. It's not true, because one doesn't depend on the other. So just remember that when somebody is saying that something is hot or something is due, if it doesn't rely on what happened previously, it's an independent event, and it doesn't have any bearing on what's going to happen in the future. Okay, so let me show you, I'll get to the video I'll talk about homework later. All right. So it's a short video, so pay attention.
In this example, we're given that a coin is tossed twice, and we're asked to find the probability of getting heads and heads. It's important to understand that the 2 coin tosses are called independent events, because the outcome of the first coin toss does not affect the outcome of the second coin toss. To find the probability of independent events, we first find the probability of each event, then we multiply the probabilities together. So in this problem, P of heads and heads means the same thing as P of heads times P of heads.
Okay, just so you know, for those that don't know, the P stands for probability. Okay, and whatever's inside the brackets is the probability of whatever the circumstance is. So in this case, it's probability of heads multiplied by probability of heads. So they want to understand what is the probability of this coming up twice in a row. Somebody flipping a coin and getting heads twice.
So let's start by finding the probability of getting heads on our first coin toss. Since there's only one way to get heads in a coin toss, and there are 2 possible outcomes, heads or tails, the probability of getting heads on our first coin toss is 1/2. Next, let's find the probability of getting heads on our second coin toss, which would also be 1/2. So we have 1/2 times 1/2. Now, multiplying across the numerators, 1 times 1 is 1. And multiplying across the denominators, 2 times 2 is 4. So 1/2 times 1/2 is 1/4, which means that the probability of tossing a coin twice and getting heads and heads is 1/4.
Okay, that's pretty simple. And remember, these are dependent events. Okay? Well, a little slow. Okay. So then you can have dependent events. Dependent means they can be affected by the previous events. So an example is drawing 2 cards from a deck. After taking 1 card from the deck, there are less cards available, so the probabilities change. So let's look at the chances of getting a king. So for the first card, the chance of drawing a king is 4 out of 52 because there are 4 kings. It doesn't say what suit it is. It just said drawing a king. If you wanted, say, the king of diamonds, it would be 1 out of 52 because there is only 1 king of diamonds. But for the second card, if the first card was a king, then the second card is less likely to be a king, as only 3 of the 51 cards left are kings. Okay, does anybody not understand that? Okay, this is also called probability without replacement. So in some cases, some people would put the card back into the deck again, and then you'd have a number out of 52 instead of 51. So if the first card was not a king, then the second card is slightly more likely to be a king, as 4 out of 51 left is a higher probability than 4 out of 52. And replacement, when we put each card back after drawing it, the chances don't change as the events are independent without replacement. So the chances will change and the events are dependent. All right, let's look at the video on that. Sorry, everybody. Oh, wrong one. I got to say, okay. There, I tried to line it up, and that's what happened. Okay.
To tell the colors apart. If he chooses one sock and puts it on, then chooses another sock, find the probability of the following event. P of brown, then brown. In other words, we're asked to find the probability that Andrew chooses a brown sock, then another brown sock. It's important to understand that when Andrew chooses the first sock, he puts it on. So when he chooses the second sock, there's 1 fewer sock in the drawer. Therefore, the outcome of the first event affects the outcome of the second event, which means that these are dependent events. To find the probability of dependent...
Okay, just want to make sure everybody, is there anybody that doesn't understand why it's a dependent event? Everybody gets this. Okay. This is called without replacement because Andrew takes the brown sock that he took out first, puts it on, so that sock is not part of the second drawing. Okay, so there's no replacement. He's not putting it back in.
Events, we first find the probability of each event, then we multiply the probabilities together, just like we did when finding the probability of independent events. However, we have to be very careful when finding the probabilities. So let's first find the probability that Andrew chooses a brown sock. Since there are 4 brown socks in the drawer, and there are 8 plus 4, or 12 total socks in the drawer, the probability that Andrew chooses a brown sock is 4/12, which reduces to 1/3. Remember to always reduce if possible when finding probability. Next, let's find the probability that Andrew chooses a second brown sock. And here's where it gets tricky. Remember that when Andrew chooses the first sock, he puts it on. So if he has already successfully chosen a brown sock, there are no longer 4 brown socks in the drawer. There are 3. And there are now 8 plus 3, or 11 total socks in the drawer. So the probability that Andrew chooses a second brown sock is 3/11.
Okay, this is very important because when you're doing probability without replacement, remember you have to reduce the total from both parts. So in this example, you have 12 total socks to start with. He picks a brown sock, so it's 4 out of 12. That's easy enough. Then the second time he chooses the sock, there's 1 less brown, so it's 3. It's 4 minus 1. And there's 12 minus 1 total socks when you're figuring out the probability, so 3/11.
Now, to find the probability that he chooses a brown sock, puts it on, then chooses another brown sock, we multiply the probability that Andrew chooses a brown sock, 1/3, times the probability that he chooses a second brown sock, 3/11. Notice that we can cross-cancel the 3 and 3 to 1 and 1. Now, multiplying across the numerators, 1 times 1 is 1. And multiplying across the denominators, 1 times 11 is 11. So 1/3 times 3/11 is 1/11, which means the probability that Andrew chooses a brown sock, puts it on, then chooses another brown sock is 1/11. Andrew has 8 black.
Oh, sorry. Okay. So we looked at that. Okay, elementary events. So the probability of an elementary event occurs from 0 to 1 inclusively. Each elementary event has a particular probability in some discrete probability distribution having a finite sample space. On the other hand, if we talk about a continuous probability distribution, each elementary event should be assigned with a 0 probability, since there are infinitely many elementary events and only non-elementary events that have non-zero probabilities. So there are some mixed probability distributions which include both discrete elementary events and small stretches of continuous elementary events. In those cases, all the discrete elementary events possess non-zero probabilities. So an example, when a coin is tossed, the elementary events are an event of obtaining a head and an event of attaining a tail, since both cannot be subdivided further into simpler events. So those are elementary. They are single events, also referred to as elementary events. So, example 2, when 3 coins are tossed simultaneously, following are the elementary events. So they can't go any smaller, but these are the single most events you can occur. So getting 3 heads in a row, I'm just reading down the list, getting a head and 2 tails, getting a tail, a head, then a tail, getting 2 tails in a row, then a head, getting 2 heads and a tail, and getting a head, tail, and a head, getting a tail and 2 heads, and getting 3 tails. So if you're given a problem, and usually it involves cards or coins, you might have a question that asks you to give the elementary events. Okay? In this case, we have 8 elementary events if we toss the coin 3 times. Okay? Any questions about that? These are all results that you can obtain if you toss 3 coins. All the possible outcomes that you can get. Okay? So, if you want to figure it out mathematically, you have 3 coins. Okay? You have 8 events, and 2 cubed, because you have only heads or tails, gives you 8. Those are the 8 possibilities that you have. That's figuring out mathematically. Next example, when a die, that's 1 dice, is rolled, the elementary events would be a 1 through 6. Okay, because it's only 1 die. So you only have you have 6 possibilities because it's only 1 die. So when a sack contains few balls or marbles of different colors and 1 ball or marble is drawn at random, the event of getting a ball or marble of a particular color is an elementary event because it's the only time it can happen. That's it. If a card, example 5, if a card is drawn at random, then the event of getting an ace of spades, getting a king of hearts, a 5 of clubs, or a queen of diamonds, etc., are the examples of elementary events. Okay? Any questions about that? All right, moving on. Okay. All right. So, sample space. The sample space is the collection of all possible outcomes of a probability known as the sample space. So in that pre-example of tossing the 3 coins and you had all those possibilities, the 8 possibilities, that is what is referred to as the sample space. Okay, probability concerns itself with random phenomena or probability experiments. These experiments all are different in nature and can concern things as diverse as rolling dice or flipping coins. And the common thread that runs through these probability experiments is that there are observable outcomes. You can see what happens. Okay, there's nothing hidden from you. And the outcomes occur randomly, and it's unknown prior to conducting the experiment. In this set theory formulation of the probability, the sample space for a problem corresponds to an important set. Since the sample space contains every outcome that is possible, it forms a setting of everything that you can consider. So the sample space becomes the universal set in use for a particular probability experiment. So I'm going to show the video on sample space. Sorry, I'm trying to move. Okay. Whoop. Sorry about that. Okay.
Girl, then a boy, girl.
Sorry, I'll start at the beginning there.
Sample space. And all sample space is the total, or it's not taking total, just put all the possible outcomes. So what's the sample space? I'm just gonna have this represent sample space. What's the sample space of having one kid? One kid. Well, the sample space of having one kid is either a boy, so you could have a boy if you have one kid, or a girl. That's the sample space of one kid. What about two kids? Two kids. The sample space of two kids, well, that's just, you could have a boy first and then a boy again, a boy first and then a girl. You could have a girl first, then a boy, then a girl, and a girl. So the sample space of that is these four. Now let's do the sample space of having three kids. And I just really want to point out, you could have a boy first, and then a boy first, then a girl first, then a boy, girl first, then a girl. So that's the sample space. It's those four outcomes. Now let's go to three kids. Three kids. What's the sample space of having three kids? Well, you could have a boy first, then a boy, then a boy. So that's one outcome. You can have a boy first, then a girl, then a boy, girl, a boy, girl, and it would go on to maybe just having a girl, and a girl. The sample space is this one outcome plus this one outcome plus this outcome plus this outcome plus this outcome plus that outcome plus that outcome plus. So it's 1, 2, 3, 4, 5, 6, 7, 8. So it's eight total possible outcomes. So the sample space size is 8. So this one was 2, this one was 4, this one was 8. So if we wanted to have four kids, all we have to do is multiply.
Okay, so that was my question. What would be the sample space if you had four kids? Can anybody tell me what they think the sample space? Look at the first three. This is mathematical, so it shouldn't be a problem. You don't have to count on your fingers. Okay. Regil and Wellington say 16. Amir 16. Anybody else? 16. Does anybody think other than 16? Okay. So this here, your mathematical ability comes into play. Okay, you don't have to draw all this out because you can figure out the sample space mathematically. All right.
Multiply 8 by 2 are simply what we did here. We had 2. Here we had 2 times 2. And here we had 2 times 2 times 2, which is 8. 8. So 4 kids is 2 times 2 times 2 times 2, which is 16. Or simply 2 to the number of times you want to have kids, or to the number of kids. So if we wanted to have 100, you could find the sample space size by 2 to the n, and that's for kids.
Okay, so if a couple wanted to have 5 children, what is the sample space going to be? 32. 32. Well, at least a couple of you are attempting this. Does the rest of the class understand why it's 32? Yeah, it's 2 to the 5th. So it's just a little help that you can figure out what the sample space is by knowing what the numbers are that you have.
Now let's go to flipping a coin. Let's say you flip a coin one time. Flip one time. So what's the sample space of flipping a coin one time? Well, you can get heads, or tails. But if we flip it twice, 2 flips. Sample space of that is just equal to heads. You can get heads on the first flip and then heads again. You can get heads on the first flip and then tails. You get tails and heads, and tails and tails. So that's the sample space for flipping a coin 2 times. And it's the same idea if we were to flip it 3 times, it would look something like this. The 3 sample space of flipping it 3 times would look heads, 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 or tails, 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 or tails, heads, tails, and it would just go on. So let's go on to rolling a die. 1, roll 1. Let's say you roll 1 die. What's the sample space of rolling a die once? Well, what are all the possible outcomes from rolling a die once? It could be 1, you can get 1, you can get 2, or 3, 4, 5, or 6. So that's the sample space of rolling it 1 time. What about if you roll 2 times? The sample space of rolling it 2 times is equal to 1. So the first time you roll it, you could get a 1. If you roll it again, you could get 1 again. You could roll a 1 the first time and get 2 the second time. Or you can roll a 1 the first time and get 3 the third time. And go on like that. This actual size is 36. So the sample size is 36. So, I mean, at the end you'd have 6, 6. That is the sample size of rolling a die twice. And notice that is just 6 to the number of times you roll it. So 6 squared is just 6 times 6. That's just 36. Now what about this? What's the sample space for all the possible license plates? If we assume that these are all letters, so this can be A, B, C, and that all these can only be digits, so 0, 1, 2, 3, so on. So what's the sample space of that? The sample space could be A, B, C. So you can have, actually, could be A, 1, 1, 1, A, 1, 1, 2, A 1, 1, 3, and it just go on for about 17.5 million. We can find that out by just multiplying all the possible outcomes for this one, which is 26, times all the possible outcomes for this one, which is 26, times all the possible outcomes for this, which is also 26, and all the possible outcomes of that, and that. That's just 10, 10, and 10. And
Okay, does everybody understand how he's getting those numbers? Anybody see where he's getting the numbers from? Okay, he's using the alphabet. There's 26 letters in the alphabet. He's using digits from 0 to 9. There are 10 digits. That's where he's getting the 10 from.
if you multiplied all these together, you get 17.5 million. So this sample space is huge. Now let's go on to picking one card out of a deck. One card. What's the sample space of picking one card out of the deck? Well, that is just depending on what you're picking out. You could pick out the Ace of Hearts, or the Ace of Diamonds, or the Ace of the Clubs, and so on. You could maybe pick out the Three of Hearts, or go on even more, the Jack of Hearts, or assuming there's no jokers, the King of Hearts. And I mean, the sample size is 52 if you're playing with a normal deck of cards. So the sample space size is 52. Now what happens if, what's the sample space if we picked two cards, and did not put them back in? So we picked one out. So let's say the first one we got, we picked one out, put it over here, and then picked another one. What's the sample size of that? Well, what's the total number of possible outcomes for the first one? Well, the first pick could be anything. It could be an ace, the Ace of Hearts, and then it could also, the next pick could also be the Ace of Diamonds. And it would just go on forever. But it would be 52. The sample size would be 52 times 51 if we do not replace. Do not, or don't replace. So that's just the total possible outcomes for the first pick, which is 52, times the total possible outcomes for the second pick, which is 51, and that is equal to 52 times 51, so 2,652. 2,652? 2,652 possible outcomes. So the sample space of this is relatively large if you pick 2 cards and don't replace them. And the same thing would be true if we did 3 cards. 3 cards, the sample space, or sample space size, would be 52 times 51 times 50, and that's just this number times 50, times 50. So that's a relatively large sample space size. So remember, sample space is just all the possible outcomes.
Okay, we looked at that. Sorry. All right, so just continuing with sample space. So common sample space. Sample spaces are infinite in number, but there are a few frequently used for examples in an introductory statistics or probability course, like this one. So below are experiments and their corresponding spaces. Flipping a coin, we've gone through that. There are 2 elements in this sample space. The experiment of flipping 2 coins in a sample space is the sample space has 4 elements. And for the experiment of flipping 3 coins, the sample space has 8 elements, 2 cubed. So for an experiment of flipping n coins, where n is a positive whole number, the sample space consists of 2n elements. There are a total of c and k ways to obtain number of k heads and n minus k tails for each number from each number k from 0 to n. And for the experiment consisting of, rolling a 6 single-sided die, the sample space is 1 to 6, or 6. And for the experiment of rolling 2-sided dice, the sample space consists of the set of 36 possible pairings of the numbers 1, 2, 3, 4, 5, 6, or 6 squared, you get 36. And for the experiment of rolling 3-sided dice, the sample space of the set of 216 possibly triples of the number 1, 2, 3, 4, 5, and 6. Okay, so what is 6 cubed? Anybody? You have your calculator? No? I believe it's 216. So there's a way for you to find the sample space by just doing the number to the exponent of whatever you've got there. So you have three-sided dice. Sorry. Okay. So we're going to talk about unions and intersections. So the union of two sets A and B is defined as the set of all events which belong to either to the set of A or B, and the union corresponds to the logical OR and is denoted by using the symbol like a U. All right? So we have two sets of data. We have A, we have B. If you want to consider this the intersection between A and B, it's called A, U, B, where some elements of A are mixed in with elements of B, and that's where they cross over. That is the intersection. The intersection of the two sets of A and B is defined as a set of events which belong to both A and B, and the intersection corresponds to the logical and is denoted using the symbol. That's a poor example of the symbol, but it looks like sort of an N, but it's also like an upside down U. Okay, so this is the union. This is the intersection. Okay, so it's only where the elements of A and B intersect and are in the same set, and that is the intersection. Any questions about that? All right. So let me.
Familiarize ourselves with the notion of a set and also perform some operations on sets. So a set is really just a collection of distinct objects. So for example, I could have a set, let's say set X. And let's say, and I'll deal with numbers right now, but a set could contain anything. It could contain colors, it could contain people, it could contain other sets, it could contain cars, it could contain farm animals, but the numbers will be easy to deal with just because, well, they're numbers. So let's say I have a set X, and it has the distinct objects in it, 3, the number 3, the number 12, the number 5, and the number 13. That right there is a set. I could have another set. Let's call that set Y. I didn't have to call it Y. I could have called it A.
I just want to check with everybody. Is there anybody that's not familiar with the term set? It identifies a set of in our case, it's because it's math, it's a set of numbers. So is there anybody not familiar with this concept? Everybody's familiar? All right, great.
A, I could have called it Sal, I could have called it a bunch of different things, but I'll just call it Y. And let's say that set Y, it's a collection of the distinct objects, the number 14, the number 15, the number 6, and the number 3. So fair enough. Those are just two set definitions. The way that we typically do it in mathematics is we put these little curly brackets around the objects that are separated by commas. Now let's do some basic operations on sets. And the first operation that I will do is called intersection. And so we would say X intersect the intersection of X and Y. X intersect Y. And the way that I think about this is going to yield another set. This is going to yield another set that contains the elements that are in both X and Y. So I often view this intersection.
Okay, so what would be the intersection of X and Y in this sample? 3? Anybody say anything else? Everybody says 3? For those that are still, it's 3. Okay. Just confirm that.
Section symbol right here as and. So all of the things that are in X and in Y. So what are those things going to be? Well, let's look at both sets X and Y. So the number 3 is in set X. Is it in set Y as well? Well, sure, it's in both. It's in both, so it will be in the intersection of X and Y. Now, the number 12, that's in set X, but it isn't in set Y, so we're not going to include that. The number 5, it's in X, but it's not in Y. And then we have the number 13 is in X, but it's not in Y. And so over here, the intersection of X and Y is the set that only has one object in it. It only has the number 3. So they're done. The intersection of...
Okay. I just want to make sure that that is clear to everybody. And the convention is you have to use this notation. So X upside down U, or X intersects with Y, means we take what is common in X and what is common in Y to both of them. Okay? It's the intersection. And in this case, it's 3.
Of X and Y is 3. Now, another common operation on sets is union. So you could have the union of X, and Y, and the union I often view, or people often view, as OR. So we're thinking of all of the elements that are in X or Y. So in some ways you can kind of imagine that we're bringing these two sets together. So this is going to be, and the key here is that we care, a set is a collection of distinct objects. And the way we're conceptualizing things right here, this is the number 3. This isn't like somebody's score on a test or the number of apples they have. And so there you could have multiple people with the same number of apples. Here, we're talking about the object, the number 3. So we can only have a 3 once. But a 3 is in X or Y. So I'll put a 3 there.
Okay, so that is also an important concept. Even this is not similar to when we're talking about, the mode. There's 2 3s, but we're not talking about that. We're talking about the union of 2 sets. So the 3 in X is the same as Y. So you're only going to put 1 3 in the union set. All right, make sure that's clear.
A 12 is an X or Y. A 5 is an X or Y. The 13 is an X or Y. And just to simplify things, we really don't care about order if we're just talking about a set. I just put all of the things that are in set X here. And now let's see what we have had from set Y. So we haven't put a 14 yet. So let's put a 14. We haven't put a 15 yet. We haven't put the 6 yet. And we already have a 3 in our set. So there you go. You have the union of X and Y. And one way to visualize sets and visualize intersections and unions and more complicated things is using a Venn diagram. So let's say this whole box is, you could view that as a set of all numbers. So that's all the numbers right over there. We have set X. I'll just draw as a circle right over here. And I could even draw the elements of set X. So you have 3 and 5 and 12. 3, 5, 12, and 13. And then we can draw set Y. And notice, I drew a little overlapping here because they overlap at 3. 3 is an element in both set X and set Y. But set Y also has the numbers 14, 15, and 6. And so when we're talking about X intersect Y, we're talking about where the two sets overlap. So we're talking about this region right over here. And the only place that they overlap the way I've drawn it is at the number 3. So this is X intersect Y. And then X union Y is the combination of these two sets. So X union Y is literally everything right here that we are combining. Let's do one more.
Okay, I just want to check Is there anybody in the class that has not worked on a Venn diagram previously? I guess the silence means everybody has worked on Venn diagrams. Okay, great.
Example, just so that we make sure we understand intersection and union. So let's say that I have set A, and set A has the numbers 11, 4, 12, and 7 in it. And I have set B, and it has the numbers 13, 4, 12, 10, and 3 in it. So first of all, let's think about what let me do that in A's color. Let's think about what A intersect B is going.
Okay, so who can tell me what A intersect B is going to be? Four and 12. Amir says 4 and 12. Anything else? Anybody else? All right, we'll go with that.
Going to be equal to? Well, it's the things that are in both sets. So I have 11 here, I don't have an 11 there. So that doesn't make the intersection. I have a 4 here, I also have a 4 here. So 4 is in A and B. It's in A and B. So I'll put a 4 here. The number 12, it's in A and B. So I'll put a 12 here. Number 7's only in A. And then number, I guess, 13, 10, and 3 is only in B. So we're done. 4 and 12, the set of 4 and 12 is the intersection of sets A and B. And we could even, if we want to, we could even label this as a new set. We could say set C is the intersection of A and B, and it's this set right over here. Now let's think about union. Let's think about I want to do that in orange. Let's think about A union B. What are all the elements that are in A or B? A or B? Well, we can just literally put all the elements in A, 11, 4, 12, 7, and then put the things in B that aren't already in A. So let's see, 13, we already put the 4 and the 12, the 10, and a 3. And I could write this in any order I want. We don't care about the order if we're thinking about a set. So this right here is the union.
Okay. So just continuing with events. So this is just an example. If you look at the game of roulette, is there anybody not familiar with roulette? Everybody is familiar. All right. You know it. Okay. Amir, you know what roulette is? Okay. To quickly explain it, I'm sure if you've seen movies about people going to casinos, there's a wheel that is spun by the dealer, and it has a little ball, and he lets the ball go into the wheel, and it lands on a number, and if somebody picks that number, then they win. If they don't pick the number, they lose their money. Okay, so how many numbers let you win? If you bet on the red numbers and the numbers of the third column, in order to evaluate this, you have to calculate the union of set A, the red numbers, and the set B, the numbers in the third column. If B contains 22 numbers, which are comprised of 18 red numbers and the 12 numbers in the third column, so it's evident that the number of elements of the union of A, B is smaller than the sum of the individual sets, since some of the numbers belong to both sets. So remember, we're talking about the union here. So we have A, okay, the probability of winning, we have 18 out of 37, 0.4865. We have the elements of B, the probability of winning is 12 out of 37, which is 0.3243. And the probability of A and B, okay, we have all these numbers, 22, 37 is 0.5946. So the calculation of the probability has to be based on 37 numbers because of the zero field. So how many numbers win twice if you bet on red in the third column? In order to win twice, the selected number has to be an element of the intersection of the set A, the red numbers, and set B, numbers in the third column. So the intersection contains 8 numbers. Thus, you have a chance of 8 out of 37 to win twice. And here we have the probability. You have set A, 18 out of 37. Set B, 12 out of 37. If we set A intersect B, we have 8 out of 37, which ends up at 0.2162, which is a lower probability. So the probabilities of compound events or multiple events can be calculated by counting the sample points and applying the summation rule. In addition, there exist some rules to calculate the probabilities for more complex problems which do not allow to count sample points. Okay. When you go to a casino, they're not there to give you money. They're there to take your money. So this isn't very good odds. This is a 21.62% chance of winning, which is not very often, maybe 1 in 5. So just remember that if you decide to take your money and give it away. All right. Mutually exclusive event. A mutually exclusive means you can't get both events at the same time. It's either one or the other, but not both. So an example, turning left or right are mutually exclusive. You can't do both at the same time. If you are, you shouldn't be at George Brown. You should be on the circuit for trick riding. I don't know. You could split the car in half. One go right and one go left. Heads and tails are mutually exclusive when you're flipping coins. Kings and aces are mutually exclusive when you're doing cards. What is not mutually exclusive? Kings and hearts are not mutually exclusive because you can have a king of hearts like here. But you can have a king of hearts here. Okay? We're comparing different denominations here. Okay? Here are the 4 suits of aces, here are the 4 suits of kings. They're mutually exclusive. If we're saying, let's get hearts and all the kings, then there's an intersection here with the king of hearts, okay? Because it also belongs to kings, but it also belongs to the hearts. And they are not mutually exclusive, so they can be both. So I'm going to show you, get to it, the video. Mutually exclusive.
Probabilities.
The easiest way to think about probabilities and the idea of mutually exclusive events is to take a simple example like drawing one card from a standard deck of well-shuffled cards. So let's find a deck.
How did she do that?
All right, we're shuffled. So now if I lay out these 52 cards and I pick one at random, what's the probability that I end up with the ace of hearts? Well, this one wasn't it. The probability is just 1 out of 52. That much is pretty obvious. If I repeat the experiment and I say, well, what's the probability now? I'm not curious about the probability of ace of hearts, but for king of diamonds. What's the probability? Well, again, it's 1 out of 52. There is only one king of diamonds in this whole deck. Now, let me ask you a secondary question. If I was to shuffle the deck, lay them out in front of me, and pick at random, what is the probability that the card I pick is either an ace of hearts or a king of diamonds? Well, there are two good options, and I don't know if this one is either of those, but the overall probability will be 2 out of 52. It's just the sum of the two choices. Now that worked out because those two choices were mutually exclusive. It would be impossible for the card that I pick to be both the ace of hearts and the king of diamonds at the same time. It's just one card. So now let's phrase a more general question. Again, suppose that I'm just picking one card from a shuffled deck of 52 cards. And I ask, what is the probability that the card I pick is an ace? Well, it could be an ace of hearts or an ace of...
Okay, so can someone figure out what is the probability of picking an ace out of a deck of cards and reduce it a mere? Remember, that's not satisfactory. You have to reduce 4 over 52 if you can reduce it. 1 over 13, which is, what's the percentage? Okay, and that, what is the percentage, John? 7%. Okay, Wellington has 7.6%. Okay, I'm just going to mention something here. You did it wrong. Okay. Anyways, it brings up a point. On any of your, your presentation, your test, your homework, and case study, if you're going to be using decimals, I want you to use a number to 2 decimal points. Okay, which means if it goes more than 2, do you all know what the rules of rounding is? Can someone tell me what the rule of rounding is? No one? No one knows the rules for rounding? Okay. If you have a number, 3.562, and I want to round it to 2 decimal points, what is it? 3.562. When you round it to 2 decimal points, what is the number? Right, 3.56. Wellington, you're correct. If the third number is 5 or more, you don't round it up, you round it up. Unless you're making, hamburgers or something. And 4 or less, you round down. Okay, so in this case, it was 3.562. 2 is 4 or less, so you keep it at 3.56 when you round it. Has everybody done that? Is there anyone that has not done it? Sorry, I don't ask in the negative, but anyways. Is anybody that has not done rounding before? Everybody have? Okay, we'll just continue with the video.
Spades or an ace of diamonds or an ace of clubs. So there are 4 good choices, and that means that my probability is 4 out of 52. If I then ask what is the probability that the card I end up with was a heart, now I have to think about all the different options, and there's a 2, a 3, all the way up to 10, and there's also Jack and Queen and King and Ace. So that gives me 13 out of 52. Okay, now let's ask the similar question, where we say, what is the probability that the card that is either an ace or a heart? You may be tempted to just go ahead and write 4 out of 52 plus 13 out of 52, but that would be wrong. The reason why it's wrong is because the ace of hearts got counted twice, once as being an ace and once as being a heart. So let's see why this works. Let's think about...
Okay, does everybody see that? John, do you see that? You can't count it twice. You understand? Okay. Anybody else? Anybody confused by that? So it is not 13 out of 52. You said 25%. Yeah. Okay.
The set of all the outcomes which give us an ace. And what we're going to do is actually draw a Venn diagram where in the box we have all 52 cards. The blob on the left-hand side just represents all the ace cards. And then let's draw another blob which represents all of the heart cards. Now notice that I have those overlapping. We know that there are actually 4 aces in total and there are 13 hearts in total. But there's 1 ace of hearts. So that is in the intersection, in that overlap zone. What that is that there are 3 other aces which are not hearts, and there are 12 other hearts which are not aces. So that's the Venn diagram which explains the example. Now, if I ask the question, what is the probability that my card is an ace or a heart? All I have to do is go ahead and add up anything that belongs to one of those things, one of those pieces. That's the 3, the 1, and the 12. And what do I get? 16 out of 52. Okay, so we're getting somewhere. Now we see this is the correct probability, and by the way, that's roughly 30.8. In general, if we have 2 events, let's call them A and B, and we want to know the probability that A or B happens, that's equal to the probability that A happens plus the probability that B happens minus the probability that A and B both happen. If we think about this equation in terms of the example we just saw, this is like saying the probability that the card we pick is an ace or a heart is going to be equal to the probability that's an ace plus the probability that's a heart minus the probability that it's both. So it's an ace of hearts. And that's exactly what we see. That gives us 4 out of 52 plus 13 out of 52 minus 1 out of 52. Notice we get the same result. Let's see why this makes sense in terms of the Venn diagram. Well, if we think about calculating up all the things that belong to A, let's shade those in, and we've counted them all once. Now we add up all the things that belong to B, in this case hearts, and we shade that up. We count all those things once as well. But notice something, and that was in the intersection got counted twice. And that's no good. We need to remove that count once so that we've counted those things only once. We need to make sure that everything in the set we have is counted exactly once. That's why this equation makes sense. So you may have heard that if you have 2 events A and B which are mutually exclusive, then the probability of A or B is equal to the probability of A plus the probability of B. The reason why this is because if you think about the Venn diagram, mutually exclusive means that there's no overlap. So really all we're doing is using the regular old equation and just subtracting 0 because their intersection is nothing. So in general, all you need to remember is the big equation in the purple box. And that tells you how to deal with either mutually exclusive events or events that are not mutually exclusive.
Okay, so I just want to ask if anybody does not understand what she has done. Remember, you're talking about mutually exclusive events. Okay, I don't see any comments, so I gather everybody's good in doing that problem.
Exclusive. Don't forget to subscribe for video updates. And if you like this video, don't forget
to give her a thumbs up. Okay. Okay, we saw that one. Okay, so mutually exclusive events and collectively exhaustive events. So we saw the video about mutually exclusive. You know that if you're thinking about a Venn diagram, it's two separate things. They're mutually exclusive. They don't overlap with each other. And if the occurrence of any one event means that none of the others can occur at the same time. Events that are collectively exhaustive, if at least one of the events must occur when an experiment is conducted. So the sum of all collectively exhaustive and mutually exclusive events is 1 or 100%. So you have the roll of the die, that's the experiment. You have all the possible outcomes, 1 through 6. Collectively exhaustive and mutually exclusive events. Okay? All right, sorry.
Three ideas, or in this case, the three Everyone's saying MISI wrong. It's used by strategy consultants, business leaders, and MBA students, but is everyone misusing it? First, let's quickly review what MISI is. MISI is shorthand for mutually exclusive, collectively exhaustive. So let's just show what this means conceptually. Let's say we have three distinct ideas, exhibited here by the three different color rectangles. In order to be mutually exclusive, they are each distinctly different. They don't overlap at all. Then to be collectively exhaustive, together combine the three ideas, or in this case the three rectangles, come together to complete a whole. So let's go back to the question we asked at the beginning. Is everyone saying MISI wrong? So to understand this, let's meet Barbara Minto. Barbara Minto, here pictured on the left, was one of the first female MBA hires at McKinsey and invented the MISI concept as well as the pyramid principle at McKinsey, building on many ideas, including some of the work from Aristotle in the Rhetoric. So, in an alumni article where she talked about the origins of MISI, she boldly said, "I invented it so I could say how to pronounce it." And her pronunciation, surprisingly, given that so many people pronounce it MISI, is Mies, as in Greece. So there it is. 99.9% of modern day consultants are saying MISI, while Barbara's still saying Mies. If you're curious about...
Well, that was pretty enlightening. Sorry about that, but got to the point of collectively exhaustive is you're combining, you're summing all the events. All right. Now we have complementary events. This is where two outcomes an event that are the only two possible outcomes. So an example is flipping a coin and getting heads or tails. Of course, there are no other options, and these events are complementary. Rolling a die and getting a 1 or a 2 are not complementary, since there are other outcomes that may happen, 3, 4, 5, or 6. Okay. However, rolling a die and getting a 1 or not a 1 are complementary. You have to roll either a 1 or not a 1. Does anybody have a question about understanding what complementary means? No questions? Okay. You don't get it? What don't you get, John? What is it you don't understand about a complementary event? Okay. Complementary is the opposite of whatever the event was. So if you look at it, if you flip a coin and you get a head, what is the complementary event? Okay. So the other example, I roll a die and get a 1. What is the complementary event? No. Yeah, 2, 3, 4, 5, or 6. Not a 1. Right? You can say not a 1 is equivalent to 2, 3, 4, 5, and 6. You see that? Okay. Okay.
Complementary events. Now, before we get an understanding of what that means, what we need to work out is what is the maximum probability for any event? In other words, for anything occurring. And we can actually determine that by having a look at some very simple examples. Let's have a look at our diagram here for a series of letters in the alphabet and work out some different probabilities. First one we're going to have a look at is the probability of a vowel. And in this case, we go through and identify all the possible outcomes. There's 14 of them, and 6 of those letters are vowels. So they're the favorable outcomes. So the probability of a vowel is 6 over 14. Now let's have a look at the probability of a red letter occurring. Again, the total number of outcomes doesn't change, it's still 14, but we need to identify the favorable outcomes, in other words, the number of reds. And if we go through our diagram, there are 5 possible cases of red letters. So the number of favorable outcomes is 5. So the probability of a red is 5 over 14. Now let's consider another case, which may be a bit strange, but we'll have a look at the probability of a letter of the alphabet being selected. So again, if we look at our diagram, there are 14 possible letters, but every single one of those letters is a letter of the alphabet. So the probability of selecting a letter from the alphabet is 14 out of 14. In other words, 1. That's the maximum possible probability that we can achieve. And the reason why that is because the number of favorable outcomes will never exceed the total number of outcomes. Or think of it in terms of the fraction. The top number 14 is the number of favorable outcomes. It can never exceed the total number of outcomes, because if it does exceed the total, well then clearly we've counted the total incorrectly. So the maximum probability for any event is 1. This is an extremely useful result, and we do use this when we define complementary events. Let's have a look at another example where we're trying to work out the probability that we have not chosen a red letter, or that the letter's not red. Again, we can see that there's 14 letters, and we can go through and count all the letters that are not red, and there's 9 of them. So there are 9 favorable outcomes out of a total of 14. So our final probability is that the probability of not a red letter being selected is 9 out of 14. But there's another way to do that.
Okay, I'm going to ask a question. In this example, the probability of not a red is 9 out of 14. What is the complementary event, and what is the probability? Okay, anybody else? Nobody? Okay, 5 out of 14. Okay, now, why is it the complementary event? He mentioned something in the video that's very important. That's correct, it's not a red, but what else did he say in the video? Think about it. How did you come up with 5 out of 14? Okay, what is the maximum probability you can have at any particular time? Yeah, you're sort of around it, John. What's the maximum probability? Probability, not the total. 1, Wellington, correct. All right. So if we think about it as a percentage, or we think about it as a whole number, the maximum probability is 14 out of 14, correct? So the probability that a letter is not read is 9 out of 14. The complementary event is 14 over 14 minus 9 over 14, which is 5 out of 14. The complementary event, so if you have a probability and say it's 63% for something, what is the complementary event's probability? %63. What is the complementary probability? Remember how to figure out the complementary event. What do you have to do? 37%, not 37, it's 37%. Correct. Okay, because what you're doing is you know that one event is 63%, that's the probability. You know the total percentage is 100%. So 100 minus 63% gives you 37%. So always remember that when you're doing probabilities, that it can only add up to 100%. Just continue.
Counting up all the letters that are not read can be very time consuming if there's lots of letters in our sample space. So let's have a look at the way of using complementary events. We know that the probability of selecting a red is 5 out of 14. We saw that in a previous example. We also know the probability of picking any particular letter in that oval shape is 1. In other words, the probability of a letter from the alphabet. That's the maximum possible probability. So if we know the probability of picking a red is 5 out of 14, the probability of not picking a red is 1 minus 5 out of 14. In other words, everything else. Those two events, being read and not read, are said to be complementary because by putting them together, you find everything in the sample space, and the total of two complementary events will be such that their probabilities will always equal 1. By doing that simple calculation, we can see that 1 minus 5 on 14 is equal to 9 on 14. That's the result we got in the first place when we actually went through and counted all the letters that are not read. Let's have a look at another example, and this time we'll illustrate it by tossing 2 coins, and we'll have a look at the tree diagram that gives all the possible outcomes for throwing 2 coins. We can see the last column just beyond the tree diagram has actually listed those outcomes. So there are 2 heads, a head and a tail head, and 2 tails. The question's asking us, what is the probability of 2 tails occurring? And we can see very clearly from our list of outcomes that there is 1 case out of a total of 4, which represents 2 tails. That's pretty straightforward. Let's do the same problem, but using complementary events. Now, if we can work out the complement of 2 tails and its probability, and a 1 minus that probability, we should end up with the same result. So the complement of getting 2 tails is everything else. That means getting 0 tails or 1 tail. And we can see from our diagram, there is 1 case of getting no tails. There are 2 cases of getting 1 tail. That's a total of 3. So the probability of not getting 2 tails is 3 out of 4. To work out our original probability, we then go 1 minus 3 over 4, and that gives us the same result as before. So you can see that complementary events do work in simple cases. just a matter of saying to yourself, the complement of one event is everything else. And the probability of those two events will always add up to 1.
Okay, so that's relatively easy to understand. The complementary events. No, we have no colors. Oh, my pleasure. Okay. So sampling with replacement. Okay, we talked a little bit about this. And sampling with replacement is used to find probability with replacement. In other words, you want to find the probability of some event. There's a number of balls, cards, or other objects, and you replace the item each time you choose one. So, for example, you had a population of 7 people, and you wanted to sample 2. Their names are John, Jack, Hugh, Tina, Hattie, Jacques, Des. You could put their names in a hat if you sample with replacement. You would choose one person's name, put the person's name back in the hat, and then choose another name. So the possibilities for your 2-name sample are your John John, John Jack, John Quee, Jack Tina, and so on. When you sample with replacement, your 2 items are independent. So in other words, one does not affect the outcome of the other. So you have a 1 out of 7 chance of choosing the first name and a 1 out of 7 chance of choosing the second name. And that comes out to 0.02 for each of them. And note that the probability for John and John just means the probability of choosing John's name and then John's name again. You can figure out these probabilities using the multiplication rule, which we haven't talked about yet. But what happens if you don't replace the first name before you choose the second? In other words, what happens if you sample without replacement? So I'm just going to go back, and we're just going to look at the sample with replacement. And sorry, I'm just going to get there. Oh dear. Okay. Going a little slow. This chapter is kind of heavy. Yeah. That's why we're probably going to spend 3 or 4, maybe even 5 classes on this. Okay? Because probability is not the essence of statistics, but it becomes a very important aspect of statistics, especially in business. You can see how probability, or from the classes that you've taken so far, why it's very important. I'm getting there. It's extremely slow. The afternoon.
In this tutorial, I'm going to discuss probability
Okay, sorry.
with replacement and without replacement. I'm going to use red, green, and blue marbles.
Okay. You know, when it doesn't go smoothly. Okay, so this video talks about sampling with replacement and without replacement, but we'll talk about with replacement.
I'm going to discuss probability with replacement and without replacement. I'm going to use.
Oh,
And the reason I call it strategic
sorry, that was great.
In this tutorial, I'm going to discuss probability with replacement and without replacement. I'm going to use red, green, and blue marbles. Without replacement means I take a marble out, then another marble, and then another marble without replacement. Replacement means that I take a marble out and I put it back. I take another marble out and I put it back. And I take the last marble out and put it back. So let me add some marbles to my screen here. I'll drop them all in. I wish I had some cool sound effects, but I don't. So I have 15 marbles, and let me count them one at a time now. There's 1, 2, 3, 4, 5, 6 red marbles. There are 1, 2, 3, 4 green marbles. There are 1, 2, 3, 4, 5 blue marbles. So if I add them all up together, I have 15 total marbles. I have 6 red, 4 green, and 5 blue, for a total of 15 marbles. What is the probability to pick a red marble, a green marble, and a blue marble in that order with replacement? And that's what I'm going to calculate now. The probability of a red marble is equal to the total number of red out of the total, which is equal to 6 red marbles out of 15 total, which is equal to 0.40. That's the probability of picking a red marble. And now I put it back, replace it. And then what's the probability of picking a green marble? So I take the total green out of the total. This is equal to 4 out of 15, which is equal to 0.27. That's the probability of picking a green marble. And now I will.
Okay, I'm going to ask the question. Using the complementary rule, what is the probability of picking the blue marble? Anybody still there? One in 3? 5 out of 15, that's, yeah. And what percentage is that? 33%, right. So remember, what's the complementary rule say? 1 minus, which you already know, which is 1 minus 0.67 is 33%. Okay, so let's see if that is correct.
Put it back or replace it. Okay. And then I'm going to calculate the probability of a blue marble, picking a blue marble, which is total blue out of the total, which is equal to 5 out of 15. This equals to 0.33. That's the probability of picking a blue marble. Now let me replace it. With replacement, the denominator always remains the same. In this case, it's always 15. That is with replacement. I take all these probabilities and I multiply them together. I multiply 0.40 times 0.27 times 0.33. And this is equal to 0.036 or 3.6%. So the probability of picking a red, green, and blue ball with replacement is 3.6%.
Okay, so just so everybody is familiar, he used replacement, which means when he took out a marble, he put it back in. To go in that order, you have to multiply each probability with the other. You get 0.036, which is equivalent to 3.6%. Okay, so don't get confused by the language. Remember, he is picking 3 different marbles, but you want to know what is the probability of picking the 3 different marbles in that order. Okay?
Now I'm going to pick a red marble, a green marble, and a blue marble without replacement. And I'm going to calculate the probability of that, without replacement, that is. Pick a red marble, a green marble, and a blue marble in that order without replacement. The probability of picking a red marble is equal to the total red out of the grand total. This is equal to 6 red marbles out of a total of 15 marbles. And this equals to 0.40. Now I pick a red marble and I don't put it back without replacement. Now I have 5 red marbles and 14 total marbles. Then I calculate the probability of picking a green marble, which is...
Okay, so what is the probability of picking the green marble now? 4 out of 14. 4 out of 14, correct, because you are not replacing the original red marble. So the total is now 14. Okay, Amir, 28%. Let's see if that's correct.
Is equal to the total green marbles out of the total, the new total actually, which is equal to 4 green marbles out of 14 marbles, which is equal to 0.29. And that's the probability of picking a green marble.
Now, I want you to use the complementary rule and tell me what is going to be the probability for picking the blue marble. Okay, 5 out of 13, which is figure out using the complementary rule. What should you get? Remember, what's the complementary rule say? 1 minus the total of the percentages that you have. So what should it be? And Amir, it's 5 out of 13. Okay, what is the complementary rule telling you? 1 minus what? 31%. Yes, because you're just taking 1 and minus 0.69 gives you 0.31 or 31%. Remember, it's very helpful to use a complementary rule.
Now I have 3 green marbles and 13 total marbles. And then I calculate the probability of picking a blue marble. And this is equal to the total blue out of the new total. And this is equal to 5 out of 13, which is equal to 0.38. And that's the probability of picking a blue marble.
Sorry, Wellington, it wasn't 31, it was 38.
The denominator goes down by 1 each time. It's not constant like it was with replacement. Now I multiply these 3 values together. And this is equal to 0.044 or 0.4% without replacement. Let me slide this over so you can compare with replacement and without replacement. I would encourage you to go back and think about why there's a difference in probability between with replacement and without replacement. Notice I use probability of red, probability of green, and probability of blue as my notation, and I try to simplify it so you can follow it easily. Your professor in textbook probably uses like a probability of R and even a probability of A1 like that, and that really sucks, to be honest with you. It's confusing. And the difficulty is just understanding and how to translate the probabilities. It's common to assign an event like A1 to a probability instead of writing the whole thing out each time. And that's what's going on here. And again, this notation sucks. It's confusing because you're trying to learn statistics and probability. You don't need to be translate notation. In the end, good luck. So share the knowledge, share the love. Facebook.
Okay. Anyway, sorry, nobody saw that. The complementary rule maybe works sometimes, but it not usually work. It only works when there's two occurrences. So when you know one, using the complementary rule will tell you the next one. Okay, so we did without replacement. So as you can figure out, only a few items are used here, so the odds only change a little, but larger samples taken from small populations can have more dramatic results. You can tell how dramatic the results can be by calculating the covariance, which we're not going to talk about. That's a measure of how much two items probabilities are linked together. The higher the covariance, the more dramatic the events. A covariance of 0 would mean there's no difference between sampling with replacement or sampling without. I'm not going to get into what covariance is because it probably will just confuse you. So we'll just leave that as something. Okay. We're going to stop here and continue on Friday. And as I mentioned in the announcement, the test will not be this Friday. It will probably be next Friday. So I will see everyone on Friday. If you have questions, you can come to the office hours tomorrow. So everyone take care and be safe.